Okay. So welcome everybody. Today we have Philip Mannheim. You all know Philip. It's second talk in the series, and this one will be about Goldstone bosons and the Englert-Brout-Higgs mechanism in non-Hermitian theories. So whenever you're ready, Philip, you can start. And I start with a question: why is Kibble missing in the title?
Oh, he'll appear later. He'll appear later in the talk because
Okay.
he hasn't. Because he has. Let me say this. Okay, very quickly. The original paper on how gauge bosons become massive through a Goldstone boson was written by Englert-Brout. It was followed up by a paper by Higgs, and then a few months later there was a paper by Hagen, Guralnik, Harbin, and Kibble,
Right.
in which they derived the general theory.
Yeah.
In a sense, there was the gold. If you think of Goldstone, there was a Goldstone paper, and then there was the proof, a general proof by Goldstone, Salam, and Weinberg. And essentially, the Guralnik, Hagen, Kibble paper plays the same role vis-a-vis the Englert-Brout-Higgs mechanism as the Goldstone, Salam, Weinberg paper plays vis-a-vis the Goldstone boson. And in fact, since you've asked me, this talk is going to be about when those theorems don't hold. And it turns out that there's an exception.
But
okay.
Sometimes they do hold. No.
I'm going to tell you when they do and when they don't.
Yeah.
Okay. All right. So first of all, hello,
Could we
everyone.
all switch off our cameras now because Philip's connection is very, very shaky. So
Yes. So hello, everyone. I'm very happy to be participating in this series once again. I'm going to tell you some things that I've told before, but I'm putting them in a different context. So bear with me if some things sound familiar. Okay. Antilinear symmetry, we all know what it is. With the advent of Pt theories, a new chapter was opened up in quantum theory. That's, I mean, I can't say it any stronger than that. Specifically, Carl Bender and Betcher found that p squared plus ix cubed had an energy spectrum that was completely real. Now, while this was a surprise, it did not actually violate any law of quantum mechanics, since while Hermiticity implies reality, there's no theorem that says that a non-Hermitian Hamiltonian could not have a completely real eigenspectrum. So Hermiticity is only sufficient for reality. All the same, if a non-Hermitian Hamiltonian does have a real eigenspectrum, there has to be some reason. And Bender and Betcher identified the reason to be that this particular Hamiltonian, the p squared plus ix cubed, had an anti-linear symmetry, which we all know is Pt. P is parity, T is time reversal. And gradually it was realized that anti-linearity was the necessary condition for reality. And I'll give you the proof in a moment. And the necessary and sufficient condition is that H have an anti-linear symmetry and that its eigenstates be eigenstates of the anti-linear operator that H commutes with. So that's how we can get to real eigenvalues, but as you all know, there's more to Pt. How does anti-linearity work? Just consider the eigenvector equation given in equation 1. id by dt of psi is h psi, which is e psi. Replace t by minus t and then multiply through by a, and you get equation 2. And if a to minus 1 is h, then HA acting on psi is E star. And this was already shown by Wigner, who discussed time reversal, which is an antilinear symmetry. He says the energies can be real and have eigenstates for which A of psi of minus t is psi of t, or they can be in complex conjugate pairs, E and E star. And that's the two realizations that Wigner identified. However, there's something goes on in between. Namely, when you make the transition from case 1 to case 2, you go through an exceptional point. And that's what I'll be talking about in reference to the Goldstone theorem. Now, Suppose the converse. Suppose we're told that the energies are real or in complex pairs. Then not only would E be an eigenvalue, E star would be 2. Hence, we can say HA is E star A, and we obtain AHA to minus 1 minus H, A psi of minus T is 0, which means if the states are complete, then AHA to minus 1 equals H is an operator identity, and then H has an antilinear symmetry. And that's why antilinearity is both necessary and sufficient. I'm going to go through a simple example, and the reason I'm going to do it is because it's going to show up again in a few moments. We take a simple 2x2 matrix where A, B, and C are all real. This matrix is not Hermitian, but it does have a PT symmetry. You can set P as sigma 3, T is K, where K affects complex conjugation. And the eigenvalues of n, you just calculate them, are C plus or minus A squared minus B squared to the half. So if A squared minus B squared is positive, then the eigenvalues are real. And if A squared minus B squared is negative, the eigenvalues are in a complex conjugate pair. Just as we saw a moment ago, that's what always happens to a non-Hermitian but PT symmetric system. However, if A equals B, the matrix N only has one right eigenvector and only has one left eigenvector, despite having two solutions to the eigenvalue equation, both with lambda equals C. So the matrix equation mod M minus lambda I is a two-dimensional matrix and still has two solutions, but they are equal. We can check from equation 7, we can check that the state AB, the column AB, is an eigenvector, but with a constraint, and that is that B has to be equal to IA. So that means there's only one right eigenvector. But since this is not a Hermitian system, the matrix can act to the left. And by the same reasoning, you only get one left eigenvector. Where does the other eigenvector go? The eigenvector is no longer an eigenstate of the theory. However, and this will be the important point for what comes in the future, if we take the one left eigenvector that there is and the one right eigenvector that there is, their overlap is 0. And that means that the only eigenstate of the Hamiltonian that does exist is a 0 norm state. And we'll come back to that. So when this happens and a matrix is not diagonalizable, it was first discussed by Jordan, and it's known as a Jordan block situation. Now, what's interesting for this case is the Hamiltonian, the matrix is not diagonalizable, but all the eigenvalues are real. The only values are C, and C is real. And so this is manifestly non-Hermitian and manifestly all eigenvalues real. And so this shows you that really, once you allow for non-Hermitian Hamiltonians which have a PT symmetry, then the whole situation is a lot richer. Okay, now, diagonalizing, well, you can introduce an operator S and an operator S to minus 1, and you find that when you apply ns to minus 1 to n, you make it diagonal. You make it diagonal whether a squared is greater than b squared or less than b squared, but if a squared is equal to b squared, then this operator no longer exists. So the statement that the Jordan block situation is missing an eigenvector is the statement that there is no matrix that will diagonalize this, n when A is equal to B. What are the eigenvectors of n? The right eigenvectors are the columns of S to minus 1, and the left eigenvectors are the rows of S. Okay, and this just to show you that you can't diagonalize. Okay, now, so if we're going to replace hermiticity by some anti-linearity requirement, then what is going to happen to other standard quantum results that rely on hermiticity? How many of them still hold? So I looked at the issue of the Cpt theorem, where C is charge conjugation, and it was derived usually using hermiticity. And that's always puzzled me, because one of the big achievements of the Cpt theorem was to show that the K plus and the K minus particle-antiparticle lifetimes were equal. But the lifetimes are only non-zero because the states aren't stable, in which case, how could the Hamiltonian, if it were Hermitian, have non-stable states? So there had to be some extension of the CPT theorem to non-stable states. And you immediately realize, well, of course, with PT, you can have complex eigenvalues. And therefore, there had to be some connection between what we've just been discussing and the CPT theorem. And then I was able to show that you only under two assumptions, complex Lorentz invariance, namely invariance under the proper Lorentz group, and probability conservation, the Hamiltonian would automatically be CPT symmetric. And so those are the two ingredients that you need for CPT. Now, if you're in a non-relativistic system, you're below the threshold for charge for particle creation, so you can ignore C, and CPT defaults to PT. And therefore, the PT program is on a very secure theoretical footing. And it's not an accident that physical systems that have been explored over the last 20 years exhibit PT structure, because PT is allowed by Lorentz invariance. And therefore, it's a perfectly valid approach to the theory. So if the CPT theorem can go through, what about the Goldstone theorem? Does it need hermiticity? Well, that was what Alexandra, Ellis, Millington, and Senayev addressed. And I followed it up by myself, and then they themselves later on, by asking, what about the Englert-Brout-Higgs mechanism? How does that work in a non-Hermitian context? And so that's what I want to describe today. Okay, so in order to begin, we need a non-Hermitian model with a continuous global symmetry. The Alexandra, Ellis, Millington, and Senayev introduced two charged scalar fields. They took the following action, and you'll see there's an m1 squared and a minus m2 squared, which is characteristic of a double well potential. m1 squared, m2 squared, mu squared, and g are all real. G has to be positive because it's negative in the action, which means it's positive in the Hamiltonian, and that provides you with a double well potential. Now, they put in this interaction term. Now, they said that the star would denote complex conjugation because it was, for them, it was Hermitian conjugation, since the two scalar fields didn't possess any internal symmetry index. The action is not invariant under complex conjugation, so it's not Hermitian. But it is invariant under the following CPT transformation, and thus it does have an anti-linear symmetry. And therefore, we know ahead of time that the mass matrix must either give us real energies in complex conjugate pairs, or possibly an exceptional point. And we'll see that all three of them occur. Take the action, and you apply a global, namely alpha constant, transformation on the phi1 and phi2 in the usual way, and you generate a Noether current, and that Noether current is conserved in solutions to the equations of motion. So that's the model. And the thing I want to point out to you is there's no phi2 star phi2 term here, just phi1 star phi1. Okay, now to study the equations of motion, I found it very convenient to work in the component basis, namely phi1 is chi1 plus I chi2 and so on. Then in that basis, the Hamiltonian takes this form, and now lo and behold, there's an I mu squared term. We generate this I, and so this now has exactly the same structure as the p squared plus ix cubed theory, and that's tipping us off that we're going to get all of the PT solutions. Equations of motion, you can derive them directly just by doing the variation with respect to the fields. Got 4 fields, we get 4 equations of motion. Now, if you look at these equations of motion are not invariant under complex conjugation. And Alexandra, Ellis, Millington, and Senayev pointed that out. We will have to address that point, but let's leave it for the moment, because it's going to turn out that it's not going to affect any of our conclusions. And let me just ignore that point and see how we resolve it a bit later on. And now we do the standard thing for broken symmetry. We look for a tree approximation minimum where all of these functions with the bar are constant, and we define that as the minimum. And now we take this minimum that we've just introduced, we expand about it with the hat symbol, that's the fluctuation, and then we find that the fluctuations obey this mass matrix. Now, the nice thing about this is it's automatically block diagonal, namely by choosing the component basis, we have block diagonalized the mass matrix right away. Now we've got a 2 by 2 matrix, and that's exactly the one I just discussed, namely the functions, the c plus a would be minus mu to the 4 over m2 squared, c minus a would be m2 squared, and b would be minus mu squared. So everything that we discussed in that 2 by 2 matrix now immediately applies to this situation. So now let's look at the mass eigenvalues of this mass matrix. And we find that there's lambda 0 is 0, lambda 1 is m2 to the 4 minus mu to the 4 over m2 squared, and lambda plus and lambda minus are these plus or minus square root. And they're exactly like the solutions that we had before with the c plus or minus the square root of a squared minus b squared. Okay. So for the 4 by 4 matrix, 4 eigenvalues, one of them is 0, and that is the Goldstone mode. And so what we discover that without requiring hermiticity, we have established the Goldstone theorem. Okay. And that was the objective of Alexander and his colleagues, and they were very happy when they showed that. However, they had in their paper, they only showed it for the real realization, namely where this square root function was real. And so they did not discuss the other cases, but now we can see it will also hold if we're in the complex conjugate pair solution, because making this square root function imaginary doesn't change lambda 0 equals 0. And therefore we have, I believe for the first time, a proof that the Goldstone theorem still holds, even if we're in the complex conjugate pair realization. But now something very, very strange happens. Now let's look at mu to the 4 is m2 to the 4. Suppose we set mu to the 4 is m2 to the 4. Then lambda 1 also becomes 0. So lambda 1 also becomes 0. But that's the same as saying that over here, that's the same as saying that A is equal to B. And therefore, we are in the Jordan-Bloch case. Now, why must we be in the Jordan-Bloch case? Because with one continuous symmetry, we can only have one Goldstone boson. We can't have two. So we must be missing an eigenvector. So instead of having two eigenvectors in the lambda 0, lambda 1 sector, now there must only be one eigenvector. And the only way we can only have one eigenvector is if the Hamiltonian is no longer diagonalizable. And so we've extended the Goldstone theorem, which was originally proven by Goldstone, Salam, and Weinberg, we've extended it to the Jordan-Bloch case. However, even more interesting is the following. The Goldstone boson that just survived has to have 0 norm. That's what I showed you earlier on. Namely, that was I went through this calculation to show you that the 2 by 2 matrix state had a 0 norm. And therefore, what we finish up with is we get a Goldstone boson, but it carries no probability and it's not detectable. So what we've actually done is we've evaded the Goldstone theorem because we do not finish up with an observable Goldstone boson, because the Hilbert space metric is not positive definite, and the standard proof of the Goldstone theorem was always on the assumption that the Hilbert space metric would be positive definite, because nobody ever considered any other possibility prior to the emergence of PT theories. So we find that we can actually spontaneously break a global symmetry and not produce an observable Goldstone boson. Okay. So now the next obvious step is to do exactly the same thing with a local symmetry. The Englert-Brout-Higgs mechanism was first published by Englert and Brout, and then by Higgs, and then the general theory was worked out by Goralnik, Hagen, and Kibble. So we introduce a gauge field A mu. We introduce a kinetic energy operator for it. F mu nu is d mu a nu minus d mu a mu. And we have an action now where we have exactly as we had before, only this time we minimally couple to the gauge field. And as before, we have a symmetry, but now we can make alpha a function of x. We can have a local symmetry with the gauge boson taking care of the derivatives of alpha of x that appear in the d mu phi type terms. And now this is locally gauge invariant. It has a continuous local symmetry. It's CPT invariant because we have an I here and an A mu. An I and A mu are both CPT odd, and therefore the CPT symmetry has not changed. Weinberg proved a general theorem in his book that spin 1 fields have odd CPT, integer spin, even spin fields have even CPT. So that theory is still CPT symmetric, and therefore it still has an anti-linear symmetry. We proceed as before. We go into the two components, into the component basis, the chi1 and the chi2, and we get this action. And now we go into a minimum, the same minimum as before. Nothing changes. That's standard for the Higgs mechanism, the Englert-Brout-Higgs mechanism. And we read off the mass of the A mu, and that's what we get. So by working through this theory, we can see that we can produce a massive gauge boson. And now we're very, very happy to see that the Englert-Brout-Higgs mechanism goes through even if the Hamiltonian is not Hermitian, but has an antilinear symmetry. Now let's look very, very carefully at the mass because it becomes very interesting. It contains a term that goes like 1 minus mu to the 4 over m2 to the 4. But we saw a moment ago that if mu to the 4 is equal to m2 to the 4, then the gauge boson becomes 0 norm. And the theory becomes Jordan-Bloch. And what happens is that the gauge field stays massless if mu to the 4 is m2 to the 4. So we have spontaneously broken a local gauge theory, and yet we've produced a gauge boson that stays massless, even though we've broken a continuous symmetry. So what happened to the Englert-Brout-Higgs mechanism? Where did it go? Well, the answer is when mu to the 4 is equal to m2 to the 4, let's just remember a moment ago, we looked like we had 2 Goldstone bosons, but of course we can't have 2 Goldstone bosons, we can only have a maximum of 1, and therefore what we finished up with was the one that we did finish up with was 0 norm. But since it was 0 norm, it was not associated with a positive definite Hilbert space. So the standard proof that the gauge boson must become massive fails because that proof was only established for a positive norm Hilbert space, where a positive norm Goldstone boson can become the third component of a then massive gauge boson. In other words, the 2 regular components of the massless gauge boson are both positive norm, and if they are to combine with the third one and make a massive gauge boson, that third state would have to have a positive norm as well. But in the Jordan-Bloch situation, it doesn't happen, and consistently the gauge boson stays massless because there's no third positive norm state that can join it, that can join its 2 transverse states and give you a massive gauge boson.
Can I ask a question? What happens when lambda plus or lambda minus becomes 0?
Nothing in particular.
Okay.
Well, they can't both become 0. Unless,
well, one of them can become 0.
No.
Yeah.
You always have to have a complex conjugate pair. So what you're wanting to do is to make this thing vanish. Okay, now the question you're asking, we haven't looked at, is can you make this term vanish and make that term vanish simultaneously?
Yeah.
And the answer is no. In fact, I wrote it this way to show you. If you set that one equals 0, then you've got this piece left over.
I think this is possible. This is possible. I mean, we have several papers, Takanobu Taira and myself,
okay,
on the same subject. You didn't really take note of this, where this can actually happen, and this is the most interesting situation.
Okay, good.
Yeah, so I mean, what he's saying is, it's not that you make these individual terms 0, but for example, you make lambda minus 0, where the first term, first hold expression is cancelled out by the second.
Exactly.
Yeah.
Yes, oh, but okay, you make lambda minus 0, but then lambda plus becomes real.
Yeah.
I pick a mu so that they vanish.
Yes, that's right. Okay, yes, yes, you can do something with this sector as well. Yes, but you can't finish up with more than one Goldstone boson. In other words, the question is, can you make lambda 1 0 at the same time as you make lambda plus 0?
Well, actually, at that point, the Goldstone boson, the Goldstone theorem breaks down.
Yeah,
it doesn't break down at the exceptional point, but at that point, actually, it breaks down, and not at the exceptional point. That's what we found.
Oh, okay, good.
It's quite different.
Okay, so if I want that one to be 0 and that one to be 0, but you want these two to be equal. Okay.
And you didn't actually identify the Goldstone bosons. You didn't write them down, no? In terms of the original fields.
Yeah, yes, here they are. I mean, these are the quantities that don't get an expectation value. These are the analogs of the Higgs boson, and these are the analogs of the Goldstone boson. The
Goldstone boson is just a component of the complex field?
It's yes, of course. I mean, that's the fields, the only fields that you can.
Oh no, it's much more complicated than that. No,
the quantity that doesn't get an expectation, the ones that get expectation values become massive. The ones
that's incorrect. You have to diagonalize your mass matrix, and the field you identify, that's the Goldstone boson. Well, that's far more complicated than that.
No. Look. I'm saying that the chi-bar 2 and the chi2 and psi1 both have 0 eigenvalue, and that's diagonal. And I'm in the chi2 psi1 basis. That's the sector. That's the one I'm looking at with the lambda 0 and the lambda 1. It's this sector. I mean, that's what I mean. This is the sector where for fields that didn't get an expectation.
Well, no.
The Goldstone boson cannot be in the same sector as the field that gets the expectation value. Mm-hmm. It has to be orthogonal to it. Mm-hmm. And that's why it's in the Higgs bosons are in the chi1 psi2 sector. That's what I'm saying, is these two are both massive. Now, maybe you can find some funny combination of these two for which yet another quantity doesn't get an expectation value. I think that's what you're trying to do. Okay, but that would require that M1, well, actually, we'd have to sit and calculate it, but I've already, that's what my whole point is, I've already diagonalized the theory. And so I know that the Goldstone boson has to be in this sector. Okay.
The interesting thing is that when lambda plus minus either of them is 0, you can't identify the Goldstone boson. It's not possible.
Well, that's
whereas at the other points, at the exceptional points and in the PT regime, it's fairly straightforward. It just works as in the normal case.
Okay, let me just point out to you. This sector here, the chi-hat 2 and the psi-bar 1, does not depend on M1 squared.
No, this I understand. You said that already.
Okay.
Yeah.
The lambda plus and the lambda minus do depend on M1 squared, and therefore they're in this sector. Now, whatever you do in that sector does not change this sector because the theory is block diagonal. So that's all I'm saying. Okay, let me say this. What I'm showing you is what I've found. I'm happy that people can push this even further. That's fine. I mean, I think this is a rich model, and there's more to learn. But the only point that I'm making, which is that the Goldstone is in this sector, and this sector becomes Jordan block if mu to the 4 is m2 to the 4. And then something very unusual happens. I think it's unusual, is that the gauge boson stays massless. And I think that's never been discussed in the literature before. Okay. So now let's go back to the complex conjugate puzzle. So we have these equations, and if I complex conjugate them, I get I goes to minus I, and these equations are not complex conjugate invariant. Now, Alexandra, Ellis, Millington, and Sainoff noted this. They noted this. And what they did was, in order to get around this problem, they changed the variational procedure so that it led to a different set of equations of motion. Now, how do you change the variational procedure? Well, the only way to do it is you have to add on a surface term to the original action, which will then constrain the fluctuations in the fields at the surface. And when they did that, they then got a set of equations that were invariant under complex conjugation. And they got the same mass matrix as the one I've just given you, and the Goldstone boson state was still obtained. Now, while doing this is non-standard for variational principles, but it's not completely non-standard, because this is what a Hawking-Gibbons surface term does in the Einstein-Hilbert action in general relativity. Let me just comment. The Einstein-Hilbert action contains not just the first derivative of the metric, but also the second derivative. Consequently, if you do a variation, then at the endpoints of the variation, you would have to hold not just the metric constant, but also the derivative of the metric. And that's an over-constrained system because it's a second order theory, and you can only hold one constraint at the beginning of the integration and one constraint at the end. So what they did was they introduced a surface term which took care of the second derivative. And then, so in other words, what the content of the Hawking-Gibbons paper is that Hilbert got it wrong. The variation of the Einstein-Hilbert action does not give the Einstein equations because you have this extra variation at the surface. So you can do it, and it's not totally canonical, but it's certainly allowed. However, nonetheless, you'd like to be able to avoid the introduction of such surface terms, because one of the things that it causes you to worry about is that it may be that to implement the Goldstone theorem in the PT case, you had to use this non-conventional variation procedure. I mean, if it worked out that way, then it would be quite surprising, but not necessarily anything wrong with it. So the question is, can we actually implement the Goldstone theorem without having to do any kind of funny variational procedure? Okay, so.
Can I say something?
Absolutely, you can say everything.
Yes, hello. Sorry, I can't see myself, but okay. Actually, we do not explicitly introduce a surface term. We take variations with respect to phi and or phi bar, and we get equations of motion which are physically equivalent. Yes. You can go from one system of equations of motion to the other by PT symmetry, but they're physically equivalent. We do not explicitly introduce.
No! I'm about to say that. I'm about to say that.
Ah, okay. Sorry. So I'll let you talk. Sorry.
No. Thank you. What I was about to say is this: you have to decide what you mean by the star symbol, and the way to define the star symbol is either as the CPT conjugate, or you've just suggested you only need to do the PT conjugate. But if you define the star symbol as the CPT conjugate, then you will get equations of motion that are automatically CPT or in your case, PT invariant. So the simplest solution is to simply redefine what you mean by the star symbol from the beginning. Now, why should I want to do that? Why shouldn't I use the Hermitian conjugate? The answer is CPT invariance, as I just showed you a moment ago, is the quantity that is holding if you have complex Lorentz invariance and probability conservation, and not hermiticity. So hermiticity is, in a sense, the wrong way to go, and it's only become apparent with the emergence of the PT program. But you should never trust hermiticity from the beginning, and I'm going to explore that in a few moments. So first of all, if we
Philip, may I ask a question?
1 second, you can ask two, but so just to repeat, and then we'll go to the question. As long as you define the star as the CPT conjugate or the PT conjugate, everything goes through as before, and the mass matrix is not modified. And so all the results continue to hold. Yes. Question.
I have two questions. How do you quantize fields with zero norm if the Hilbert space somehow or the Hamilton is not diagonalizable? And the second thing is, what is the interpretation of complex conjugate pairs in mass states if you are looking at causality?
Oh, okay. So you've asked questions that go way beyond the tree approximation. The issue that Carl Bender and I addressed was exactly, if you remember, we first wrote a paper on the Pais-Uhlenbeck theory to show that it was in the PT category, and that was in the what's called the unequal frequency mode, where any of the eigenvalues are real. Then we wrote a second paper in which we looked at the case where the two frequencies are equal, and that's the analog of A equals B in the discussion I'm providing now. And that led us to the Jordan block situation. And we carried that through in great detail, and we showed exactly how to quantize it. And the main issue is what happens to the second state, the one that no longer is the eigenvector? Well, the answer is it becomes non-stationary, but it stays in the Hilbert space. The Hamiltonian may be 2 by 2 with only one eigenstate, but it acts in a Hilbert space which is still two-dimensional. It's just that the second state is not an eigenstate, but it is necessary for the completeness of the Hilbert space. Mm. And then we have to construct wave packets out of the stationary and non-stationary combined. And then we find that the theory is unitary. So the answer is yes. We wrote a whole paper on that very question of how do you quantize when you have zero norm. And the way to do it is you start out with the non-zero, with the regular positive definite norm, but you redefine the A's and the A daggers, the creation and annihilation operators, in such a way that the limit is not singular. And we showed exactly how to do that. Now, the question here is, now let's go back to the quantization of the theory that we're looking at. The second option, instead of redefining the star, is to make a similarity transformation. And let me just introduce canonical conjugates. Dt pi 1 is dt psi 1, pi 2 is dt psi 2, canonical conjugates for psi 1 and psi 2, and define this similarity transformation. And then we find that psi 1 goes to minus I psi 1, pi 1 goes to I pi 1, psi 2 goes to minus I psi 2, pi 2 goes to I pi 2. And then the psi 1 pi 1 and psi 2 pi 2 commutators are preserved. Therefore, this is a perfectly permissible transformation which does not modify the content of the theory. We apply it to the I that I just introduced a moment ago. We apply S1, Si1, Si2, S minus Si2, S minus Si1. And we get a new function, and here it is. So we can proceed as we did before. Nothing can change because a similarity transformation cannot change the mass matrix, and therefore not the mass eigenvalues. And we get this new expression. And then we could work with this expression. But now comes, we do the stationary variation of this theory, and now you can see that everything is perfectly okay. There are no factors of I, and everything is well defined. And everything's invariant under complex conjugation. So this time you don't need to reinterpret the star as the CP transformation, though of course you still can, and you still should, but nonetheless, nothing's changed. However, we now have a brand new problem. If we look at I prime of chi1, chi2, psi1, psi2, and all these fields are Hermitian, and the chi's and the psi's commute with each other, and the mu squared is real, then this is a Hermitian Hamiltonian, a Hermitian action. And therefore, after all this work, we found out that we've got an I that's Hermitian, all of its coefficients are real, its fields are Hermitian. So have we just recovered the standard Goldstone theorem after all this effort? Have we really gained anything? Or could I just have done the similarity transformation in the first place and said, look, actually, this is the normal Goldstone theorem. And it turns out we've not just discovered the standard Goldstone theorem. No, we have not, because appearances can be deceptive. Hermiticity cannot be determined by inspection. And why do we know that the theory is not Hermitian? Because we know the mass matrix has all three of the PT theory realizations. Depends on the values of the parameters. All eigenvalues real, eigenvalues in complex pairs, and mass matrix not diagonalizable. And yet, the action looks like it's Hermitian in all of those cases. And yet, when we explore the theory and we determine the solutions, we find that we're definitely not necessarily in a Hermitian situation. and yet the Hamiltonian looks Hermitian. Therefore, hermiticity cannot be determined by inspection. Hermiticity is a property of the full Hamiltonian, not of the individual terms in it. And that, whether the full Hamiltonian has hermiticity, depends on boundary conditions. And this is the secret of PT. Let's just look at P squared plus.
Sorry, Peter, can I just put in, Philip, is that a bit like P squared minus x to the fourth?
Yes.
It looks Hermitian, but it depends on how it's defined.
Yes, of course. No, I'm going to. I fully agree, Hugh. This is always the case. Things that look Hermitian aren't necessarily Hermitian, and things that don't look Hermitian may become Hermitian under a similarity transformation. So what we've seen is with the Alexandra, Millington, Ellis, and Senayev action, it didn't look Hermitian. And yet when we made a similarity transformation, suddenly it did look Hermitian. But except we know that it can't be because it still has all of these realizations. And what does it mean to say looks Hermitian? Well, if you take operators P and X are Hermitian when they act on their own eigenstates, namely on the states for which you can throw away surface terms in an integration by parts. However, what matters is how do P and X act on the eigenstates of H, not on their own eigenstates. Now, in the Hermitian theory, the eigenstates of H are exactly the same as if we had P squared plus X squared, there would be no distinction. But in the PT case, the eigenstates of H are different than the eigenstates of the Hilbert space of P and X. You may not be able to throw away surface terms, and you may need to continue into the complex plane in order to do so. And that's exactly the secret of PT. It's something that you think is familiar, but it turns out that when you explore the actual eigenvectors, you find that they're not necessarily ones that are normalizable that you can throw into surface terms away. So hermiticity is a property that's determined jointly by the operators and the states. You can say that P is Hermitian, but only when it acts on its own eigenstates. There's no meaning to saying that P is Hermitian in an arbitrary case. You have to specify the states, and you have to be able to throw away surface terms. On the other hand, anti-linearity you can determine by inspection, as that does depend on the individual terms in a Hamiltonian. Anti-linearity is determined by the operators alone. And therefore, H is P squared plus IX cubed is PT symmetric regardless of boundary conditions. And that's the distinction. Now, this distinction between
Jean Alessandro has a question in the chat. Jean, do you want to read it out?
Yeah, okay, I can't see the chat, so please go ahead.
Yes, thank you. So yeah, the similarity transformation here does not depend on the anti-Hermitian term mu. So in the limit mu goes to 0, you map a Hermitian model onto another Hermitian model. But did you check that they are equivalent?
In the limit in which mu goes to 0?
Yes, and then you should, because the similarity transformation is the same, because it does not depend on mu.
The similarity transformation is a property of the fields, not a property of the coefficients.
Yeah, but you expect that it depends on the model, on the coefficients which define the model, because then you can take mu equals 0 and everything is Hermitian.
I'm saying that when things look Hermitian, that's not necessarily the case. You always have to check on boundary conditions. But what I'm looking at is properties of the operators. You can always say that something is antilinear. However, some antilinear theories can be Hermitian, and you may be able to get the theory that I've been looking at to be Hermitian under certain values of the parameters. That's what you're saying. But you can't just say that. You can never tell me that something is Hermitian just by looking at it, because you haven't specified what states the operators act on until you construct those states. And that means...
Okay, I agree. I just wanted to say that I'm not sure that you deal with the same theory. When you use this similarity transformation, maybe you just create a new theory.
Oh gosh, no. It preserves the commutation relations. You see, the only issue for quantization is what are the commutation relations. Any similarity transformation that preserves them describes the same theory. There's no other criterion other than equal time commutation relations, because without them, you just have fields. You have a classical field theory until you make that the commutator of psi1 with pi1 is not zero.
So we looked at this in detail in our last article, and actually these commutation relations are not trivial at all.
Are not what?
Are not trivial because of the PT transformation. You have to define different fields depending when you act with parity, with P or T.
Yes,
and
the statement that you're making, I'm glad you've looked at this. I looked at it myself. An operator S is not necessarily PT symmetric. I mean, you have to.
Yes.
You see, if under this transformation, the Hamiltonian remains PT invariant, but it's under the similarity transform PT operator. In other words, you really, you see, we've been just using P and T for matrices, but you've really got to construct them in terms of the fields and see how they transform.
Yeah, I will not discuss this, but we have looked at this in detail.
Very good, very good.
But Philip,
yes.
The question of quantization is related also to the choice of the vacuum, and this is related to the boundary conditions. So you cannot quantize a theory with the Hamiltonian and commutational relations alone. So here I think this is a breaking point where I asked you the question, how do you quantize a theory which has zero norm? Yeah.
Okay. The answer to your question is, what Carl and I did was we first of all constructed a vacuum that had a finite norm, and that's the unequal frequency. Then we constructed the equal frequency as a limit, and that's how we proceeded. Yes, I completely agree with you. When people write down a relation like the sum on nn equals 1, they're presupposing that the states are normalizable. But you don't know that because you have to calculate the matrix. You have to look at the vacuum, and then you put in vacuum to vacuum is the integral over x and y, or let's say over x, vacuum x, x vacuum, which is the integral psi star of x, psi of x. And that is either finite or it's not finite. And in the PT theories, those quantities are not finite on the real axis. But you can continue into the complex plane, you go into a Stokes wedge, then you can make that matrix element finite. And that's the theory that you then take the limit of. A better way to say it is, you can't just write down the zero norm theory. You've got to start with a positive norm and construct it as a limit. And that's exactly what Carl and I do. Okay. Now,
Peter has a question. Peter.
Okay, good. Hello.
Hi, Philip. Hi, everyone. Yes, I just wanted to add in there. So since the vacuum was being discussed, if I think about the Fock space vacuum for the theory that you're looking at here, the similarity transformation that you've written down there doesn't actually leave the Fock vacuum invariant.
No, it will. No, what it will do is it will transform the A's and the A daggers, and I will look for a state that the transformed A annihilates.
Yeah, which is a different state, right? So it's essentially the statement that, I mean, this thing behaves, the thing that you wrote behaves very much like a Bogoliubov transformation, right?
Yes, that's right. Well, if I were in a normal vacuum case, it would just be a transformation. If I'm in the broken symmetry case, then it's a Bogoliubov transformation. Yes.
So these vacua are not necessarily equivalent vacua, right? I guess this is the statement I'm making.
Yes, but the Green's functions are equivalent. The Green's functions transform into each other. Okay. The vacuum expectation value of the field is transformed into the vacuum expectation value of the field. And if
that's certainly the case.
Yeah, I mean, for the discussion of broken symmetry, I only require that vacuum phi vacuum is a constant and remains so under a similarity transformations on the quantum fields. Green's functions are the same. By the way, that I didn't get a chance to comment to Frieda a little bit before. Frieda, if all the energy eigenvalues are real, then all the poles of the propagator are on the real axis. And then it has exactly the same causal structure as a Hermitian theory. That's as long as there are no negative energy states propagating forward in time, then you will still have causality. Now, when you go into the complex conjugate pair case, the Green's functions move off the real axis. But what you have to do is you have to deform the Feynman contour so that the same number of poles are contained within the contour as before, and then the theory remains causal. I didn't have a chance to mention that at the time. Okay, now, so now I'm going to show you.
Farhan has a question as well. Farhan, do you want to ask a question?
Okay. Please, everybody. I can't see anything except my full screen, so I'm by all means, whatever questions anyone has.
You want to ask your question, Farhan? Well, I can read it out. He says in the chat, to study hermiticity of an operator, we should examine the domain and the range of it. What happens to these sets under the similarity transformations?
Absolutely. That's all I'm saying. And I'm saying is you can't determine hermiticity by inspection. That was all I was saying. And yes, the domain, since I'm not making these operators Hermitian to begin with, the domain remains PT symmetric. And that's the only thing I need, or Cpt symmetric. That's all that I need. Okay. Now, the distinction between hermiticity and anti-linearity is even more sharply seen in the path integral formulation. We define a generating function, W of j. S for classical phi is the classical action as evaluated on every classical path that's integrated over. There is no reference whatsoever in this expression to anything being Hermitian. You construct from doing the derivatives with respect to W of j, you construct the quantum Green's functions, then you construct the quantum Hilbert space, and only then can you determine whether the quantum Hamiltonian might be Hermitian. So the hermiticity doesn't appear in the path integral. It will come in, and we'll see in a moment, it comes in a hidden way. But we can look at the classical action and make it be Cpt symmetric path by path. So we are able to define anti-linearity for a classical path integral, but we're not able to define hermiticity. So again, anti-linearity is the key. So now we even need Cpt to construct the correct X classical phi. Let's just look at a complex scalar field, d mu phi star, d mu phi. Now couple it to a classical electromagnetic vector potential. So we have two possibilities, d mu minus Ea mu, or d mu minus Ia mu. Now we're in classical theory. So in classical theory, you restrict yourself to real numbers, and therefore you would go with L1, which doesn't have the I, rather than L2, which does have the I. And of course, it's L2, which is the one that gives the right quantum electrodynamics. But how do you know to put the I in the classical theory? Well, first of all, classical physics is not even restricted to real numbers. It's restricted to C numbers, to numbers that commute, not to eigenvalues of Hermitian operators. So now we have to ask, well, we may not have to restrict to Ea mu, but how do we know to use Ia mu? Well, you could argue that Id mu and Ea mu are both Hermitian in quantum theory. Therefore, you should put that in. But you don't know that at the classical level because you haven't constructed the quantum theory yet. However, we can use Cpt symmetry because Id mu and Ea mu are both Cpt even. Therefore, the reason that we will include the I in the classical action before we even quantize electrodynamics is because the action has to be Cpt symmetric. And that is definable at the classical level. So again, anti-linearity has primacy over hermiticism.
Philip,
Hello.
may I ask a question? It's Uwe here. Hello.
Yes.
Concerning your equation 39, this path integral.
Yes.
Yes. When you're writing it down, you implicitly have here in 39, you have the division in over a certain interval in order to make the distances these small segments, and then you are plugging in a full basis between them in order to the completeness relation you are plugging in several times in the path integral implicitly in order to do it.
Actually, not at all. That's the way that Feynman derived the path integral, but he was trying to get from regular quantum mechanics to path integral quantum mechanics. What you do here is you find a complete basis of solutions to the classical wave equation, and you integrate over the complete basis. Namely, you expand phi is phi classical, that's the stationary one, plus a sum on some coefficients A times the eigenvectors of the classical problem. And then
I completely agree with you, yes, but there is a subtle point here. When you're thinking about Ix cubed theory,
yes,
we are knowing that it doesn't have a basis there.
Okay.
You don't have a Rees basis there, so you cannot use the basis property. And this is implicitly present in the path integral.
No. You're talking about the quantum basis. I'm talking about the basis of eigenfunctions of the classical Sturm-Liouville problem. That's a well-defined problem. I don't know the exact, we don't know the analytic answer, but you only need the basis of the Sturm-Liouville equation. You don't need the basis of the Schrödinger equation to define the path integral. Okay.
Okay. Let's postpone a discussion for later times. Okay.
Yeah, that would be fine. Okay. Now, it can turn out that the path integral does not actually exist if the integration measure for the paths is real, but does exist if we continue the measure into the complex plane. So I said a moment ago, there's a hidden assumption here, and that is that we're integrating over a real measure of paths. If we can, and the integral exists over a real measure of paths, the quantum theory that emerges is Hermitian. But it may turn out that this integral does not exist. That's what I said, Hermiticity can come in through the back door. It may not exist with the real basis, and you may have to continue the measure into the complex plane. Then you would finish up if you then find that after you've done that, that the path integrals then does exist. It may not exist for any measure. Unbounded and unbounded. It may exist, and then you will be in a PT theory. Now, how do we justify making such a continuation of classical theories into the complex plane? Well, if we look at the quantum xp as I relation, we let x go to e to the I theta, xp go to e to the minus I theta p, the commutation relation is preserved. So is there an analogous complex invariance in classical theory for Poisson brackets? So let's consider a 2n-dimensional theory, n coordinates and n momenta, and a generic Poisson bracket. We introduce, we write all the phase space vectors into a single column, eta. We introduce a 2n-dimensional matrix J, which is I minus I, where I is the n-dimensional unit matrix, and we can rewrite the Poisson bracket relationship as du d eta tilde j dv d eta. Now we make a phase space transformation to a new 2n-dimensional vector zeta by this transformation, mij is d zeta I d eta j, and so on. And then we find that the new transformed Poisson bracket is du d zeta mj m tilde dv d zeta. The Poisson bracket will then be left invariant for any m that obeys mj m tilde is j. So that's the condition. And now let's see what it is. We introduce generators G, which is m e to the I omega G. And we want J to obey these relations. That's the G tilde. And then we find that the generators obey this relationship, and there are two solutions. G is symmetric, and anti-commutes with J, or G is anti-symmetric but commutes with J. There are n(n-1) symmetrics and n anti-symmetrics. The total number of generators is nm plus 1 over 2, where n is too little n, and they close on the Lie algebra SPN, the symplectic group. So the Poisson bracket algebra is invariant under transformations with the symplectic group. Now, the generators obey the classical Lie algebra. Gij is the sum on k, fi, jk, gk, with real structure coefficients fjk. And therefore, you can find a representation of the algebra in which all the g's are pure imaginary, I. But the transformation is e to the I omega g. So ig is real. And if omega is real, you transform a real eta into a real zeta. And that's how Poisson brackets are used in ordinary classical mechanics. But now we notice something. Nothing in the algebra makes any reference to angles. So invariance of the Poisson brackets under canonical transformations will persist even if the omegas are taken to be complex. They never needed to be real, but we always made them real. But they can be complex. Then you will transform a real eta into a complex zeta and still preserve the Poisson bracket algebra. And therefore, complex symplectic transformations in classical mechanics will transform the classical Poisson brackets. Complex transformations in the quantum theory will transform the commutation relations, and you can still have a correspondence principle between the transformed classical Poisson bracket and the transformed classical quantum commutator anywhere in the complex plane. Now, usually this makes no difference because there's no new information in the complex plane that was not already contained in the real plane, except if you cross a singularity, a discontinuity when you do the transformation. Namely, if you go into a different Stokes wedge. So you can have one Stokes wedge where you're containing the real axis and a different Stokes wedge in which you are not. And Carl has developed the theory of Stokes wedges in PT theories. They're a central ingredient. They're tied in with the whole question of boundary conditions. And from the point of view of the path integral, the question becomes, in which Stokes wedge, if any, does this integral even exist? And that's the key to PT theory and the key to quantization. Let me just make a side remark. For four-dimensional case, it's very interesting. You can introduce the C operator of Dirac, which transposes the gamma matrices. I can take C to be in this form in the Weil basis of the Dirac gamma matrices. I can take a four-dimensional, namely two P's and two Q's, and I can write the Poisson bracket as d u tilde eta, C d v d eta, where C has to obey this condition. Now, if I now replace C by IC, C squared would be 1, because this C squared is minus 1, and it becomes very reminiscent of the C operator in PT theory. So what you would then have would be the UV Poisson bracket would be replaced by IUV, and under a canonical transformation, and under canonical quantization, it would be identified with the commutator, not with I times the commutator, but just with H bar times the commutator. So there's another possible role for the C operator. Okay, my last result is, how do we know how to do this complex transformation? Is it just complex variables? Namely, we make two-dimensional spaces from one-dimensional, or do we use the full battery of complex analysis? In classical mechanics of point particles, particles move on one-dimensional real trajectories. In the classical mechanics of waves, the normals to the wave fronts also move on one-dimensional real trajectories, and that's the for electromagnetism, that would be the Pointing vector, and those normals are the directions in which energy and momentum are transported. So we always are dealing with one-dimensional real trajectories. With an one-dimensional real trajectory, the derivative at any point on the trajectory does not depend on the direction in which the derivative is taken. So suppose we now continue trajectories into the complex plane. They will still be one-dimensional and will not become two-dimensional. But now the derivative at any point on the trajectory will depend on the direction in which the derivative is taken. However, we can avoid that problem, namely make the derivative independent of direction, if we impose the Cauchy-Riemann equations. So for a complex function f, which is u plus iv, we choose du dx is dv dy, du dy is minus dv dx. Then the derivative is uniquely defined and does not depend on the direction which is taken. And we can even write df dz is just the derivative on the real axis. And so that's the generalization of the real axis derivative in the real case. Now that f obeys this condition, it's amenable to complex analysis. Thus, the natural generalization of real trajectories in the complex plane is trajectories that obey the Cauchy-Riemann equations. It's in this sense that the classical paths in the path integral measure are to be continued into the complex plane. They have to be still one-dimensional paths, but paths that obey the Cauchy-Riemann equations. Okay, summary. The PT option for quantum theory is now well established. It in no way changes quantum mechanics. It simply takes advantage of an option that was there from the beginning, but had been overlooked. Since having an antilinear symmetry is necessary for obtaining real eigenvalues, also for probability conservation, I didn't talk about that, it actually represents the most general possible option for quantum mechanics that's allowable. In fact, anti-linearity should be used as the guiding principle for quantum theory rather than hermiticity. Namely, you should work with Hamiltonians that have an antilinear symmetry. While antilinear symmetry allows for real eigenvalues, we've got two other realizations that are completely foreign to Hermitian theories. Energies can appear in complex conjugate pairs, and Hamiltonians need not be diagonalizable at all. In this latter case, the eigenstates of the Hamiltonian have a norm that is not positive, but in fact is zero. Some familiar theorems of quantum theory that are based on hermiticity can be extended to the non-Hermitian domain, namely the Cpt theorem, the Goldstone theorem, and the Englert-Brout-Higgs mechanism. All three are found to hold in the antilinear case without needing to assume hermiticity, and are even found to hold even if energies appear in complex conjugate pairs. However, in the non-diagonalizable Jordan block case, something new occurs. While the spontaneous breakdown of a continuous global symmetry still leads to a massless Goldstone boson, in the Jordan block case, the Goldstone boson has zero norm. It is thus not observable. And more, the spontaneous breakdown of a continuous local symmetry still leads to a massive gauge boson if energies are real or in complex conjugate pairs. But in the Jordan block case, the gauge boson stays massless, despite the fact that a continuous local symmetry has been spontaneously broken. So thank you very much. And those of you who made comments on work that you had done, please send me an email so I'll know how to access all of them. I'd be very happy to receive them. I wasn't able to record everything while I was giving the talk.
I will do that.
Good.
Philip, may I ask you a question again?
Absolutely, yes.
It's Uwe again, yes.
Yes. Yes,
no, it's just, can you provide a little bit more details about this measure in the path integral, that you are thinking that it will remain more or less well accessible under your transformations?
Okay.
I am a little bit doubtful about it because when you're taking, for instance, BRSD quantization, everything works fine as long as you are working on a compact surface and your transformations here are non-compact. So you will need something like Harishchandra, a representation of group theory and all these things and characters and so on. And all these things are becoming much less simple as it might look like.
Okay, if I is compact and S is non-compact, Si S to -1 is still compact. And that's the thing I care about. I don't care about the operator. I care about the transformed action and the transformed Green's functions. But to answer your question in detail, I wrote some papers on that very point, namely, under what conditions can you make a transformation on the measure? Now, it's funny that we should ask that question, because we take it as a given that the path integral exists whatever measure we write.
No. It's absolutely not true.
I'm saying is that that's completely wrong. And Uwe, you agree with me. I'm saying that it's completely wrong. You have to find a domain in which the path integral exists before you can even discuss the path integral.
Exactly.
Now,
Yes.
that it may not exist on the real axis, and that you may not even be able to go from the real axis to the domain where it does exist, doesn't matter. What matters is where it does exist. It does not matter where it doesn't exist. It only matters where it didn't exist because you thought it did exist on the real axis.
Yes, but are you able to transform it smoothly from one of these sectors to another? I'm not sure.
Okay. The answer to your question is I've only discussed a few cases, and in those cases, and this is all in this, it was this, we wrote a series of articles for the Royal Society transactions a few years ago. It's all in there. Send me an email to remind me that you asked me the question. I'll send you the reference. It's still an open question as to whether a theory that is PT symmetric necessarily has a path integral representation. I don't think there's a general proof, but the cases that I've worked at have at least indicated to me the need to go into the complex plane. And I've also noted that when I do so, I can preserve the Poisson brackets by a symplectic transformation. And that's about as far as I know how to go. And if anyone can do that, I mean, that would be very, very good.
Yeah, but your transformation, when you're even keeping your G transformation, I remember, was it J in this exponent, or this e to the power of I G? You have this transformation there, but this operator is becoming unbounded, and you will have the highest strongly dependence on domain issues and all these things, and so everything may break down. Everything is fine as soon as it's on the compact surface. Everything is fine.
Okay,
but these things will strongly break down.
The question is, this relationship remains well behaved. That's the point. The individual operators may not be well behaved, but just think about it. In ordinary PT theory, we want to introduce this operator e to the q.
Yeah, sure.
E to the q is not e to the iq. Q is Hermitian. E to the q is not a bounded operator, but e to the q h, e to the minus q is a bounded h. And that's all we care about. Look, I mean, maybe I could say the following. Why are we even doing these similarity transformations in the first place? Because we started in the wrong place. I mean, if you can write down a path integral, find a Stokes wage in which it exists, then that's the theory. You don't care that there's some other place where it doesn't exist, and you have to use what you might regard as an unbounded operator to find a way to get there. That's just a historical accident. The theory is defined by where the operators in it exist, and not by where they don't exist.
Yes, but the transformation between one set of theories and another set of theories, and when you have a transformation which is unbounded and doesn't have a bounded inverse, everything becomes much more subtle.
Uwe, the domain in which the path integral does not exist is not a theory.
Sure. But you have several sectors.
Only the sectors in which the path integral exists are the ones that matter. Now, it may turn out there are theories where no sector doesn't exist. That can happen. But we do have working examples of PT theories where the path integral does exist in a wedge that does not contain the real axis.
Yeah, sure. But but anyway, I'm not convinced. I think there are hidden such loopholes that you even doesn't have on this. You doesn't have them on your screen. I'm a little bit afraid.
I don't mind. I'm perfectly happy for people to explore this question. There are lots of technical issues that are well worth exploring, but I stand by my original statement, which is you can't discuss a theory until it exists.
Sure, yes, I agree completely, yes.
And the fact that it does not exist under the standard treatment of real operators, Hermitian operators with real eigenvalues, does not mean that therefore it never exists.
I also agree. But when you're using transformations which are switching from existing to non-existing, it's a little bit
becoming...
becoming...
but that was only in order to find them. That was the only reason I did it, was in order to find the domain in which the path integral did.
Okay, so let's keep this for future work.
Yes, yeah. I can do two things. I can show you that in non-Hermitian theories, it's often the case that the path integral does not exist on the real axis.
Sure, yes.
Okay,
absolutely, yeah. I agree completely.
Therefore,
yes.
that theory doesn't exist, and making a transformation on it, in a sense, has no physical content. However, if I do that transformation and I cross a Stokes line, then I can find from the bad theory, I can find the good theory, but then the good theory exists in and of itself. And it never mattered that there was a bad theory from which you could find it. That, for me, that's just a historical accident.
Yeah, okay. And you are sure that in this sector that you are using then, and you are declaring it as a fine theory, that this measure is well defined there?
Yes. And the reason I can say this is because if I can, in the quantum theory, if I find a domain in which the vacuum and the excited states are all normalizable, then in the Euclidean expansion of the path integral, I pick up energies which are real, which are bounded, with coefficients which are the wave functions.
The question is how you go from the path integral to actually constructing states.
Yes.
Okay, a path integral is just a bit of classical mathematics.
Yes.
Okay, but you're trying to go from the classical integral and just pure classical mathematics to a quantum mechanics where there are states and an inner product. That's not a trivial statement.
Okay, the thing that the path
this is exactly the point, yes.
The thing that the path integral gives me are Green's functions.
No, but the Green's function depends on plugging it in.
Gives me
you have different vacuum states and all these things.
It gives me a Green's function. A Green's function is a solution to a differential equation. It gives me the Green's functions. Now, you can ask, I can look at the Green's functions and I can look at the poles in the Green's functions. And I can look at the residues of the poles. All of those things are defined from the path integral without ever specifying a Hilbert space.
Exactly.
And that is all you need.
Unless there's an ambiguity involving the norm in the path integral. I don't mean the norm, I mean the weight function in the path integral. That is, it seems to me, that is the issue. The existence of the path integral has to do with the Stokes sector in which the path in the path integral exists, okay? But the question is, there's something hidden in that path integral, and that's the question of what do you mean by d phi?
Yes.
Exactly. That's the point.
Oh, but that's where the Cauchy-Riemann equations come in. They allow me to.
So that's what I wanted to ask you about.
Yes.
Philip, you talked about the Cauchy-Riemann equation at the level of classical mechanics. What exactly do you mean by the Cauchy-Riemann equation? When you say Cauchy-Riemann equations, what you're referring to is a function of a complex variable. Okay, so we're talking about a function f of x of a complex variable x, or let's say f of z of a complex variable z. What exactly do you mean by the Cauchy-Riemann equations for the solutions to the classical equations of motion? What is z in this case, and what is f of z?
Each path is a contour in the complex plane. On each contour, you have a Cauchy-Riemann equation in the classical paths.
So when you say contour, you mean that there's a contour in the complex plane. Let's suppose that contour is parametrized by time. So a contour in the complex plane is z of t, where t is time.
Mhm.
Okay. What in that case, what exactly do you mean by the Cauchy-Riemann equations? What are those Cauchy-Riemann equations there?
No, these are just flow equations.
No. The contours in the path integral are paths between the endpoints.
Right. So they're a function of time.
They're a function of the coordinates as well. It would be phi of x. It's a function of any path that will link you from initial value of phi at x initial, t initial, to final value of phi at x final, t final. That's all I mean.
Yeah, you're just using a holomorphic extension from the real axis. That's all you're doing.
I didn't say anything else. I said that when I go into the complex plane, I've still got to keep one-dimensional trajectories, the one-dimensional paths.
Yes,
When I said contour, I didn't mean to say contour. I'm not talking about closed contours, and I'm not talking about Cauchy theorem. I just say that the trajectories are one-dimensional paths in the complex plane, and the expansion of the path integral is over an infinite basis of them. That's all I mean.
There's a question here about path integral.
Yes.
Where you're integrating over one-dimensional contours, and functional integral, where you're trying to construct Green's functions.
Yes.
And that is a non-trivial question, okay? Because that is an integral in function space.
Okay.
There's a very non-trivial connection here.
Okay, let me answer the question. Let me take W of j and do the functional variation of W of j with respect to j at x, j at y. That brings me down 2 powers of phi. I now set j equals 0, and I calculate that Green's function. I calculate that object. It's just the integral d phi, phi at x, phi at y, e to the I classical of phi. And
okay, this is a functional integral, not a path integral, because
yes, but
you're not integrating between two boundary points, and you don't have all paths between 2 points, but rather you're integrating over all functions.
Yes, that's right. The paths are interacting with j as it goes, but j is always defined that it's 0 at the initial time and it's 0 at the final time. This is the Gelman-Low adiabatic switching, I think it's called. Yes, but you see, all the path integrals do when you write the j phi's, it says the following. You start out with one configuration at t equals minus infinity. J switches on and then switches off, and then you come back to the original configuration, but times a phase. And that phase is the Green's function. And that's the only thing I'm using.
I would like to discuss this more with you, Philip.
Oh, absolutely.
This is a very, very deep issue. And
exactly.
And the Green's functions that you create by taking variations with respect to j, okay, those Green's functions are actually very non-trivial. And the question is whether or not you obtain a convergent definition of Green's functions, okay? I mean, this is extremely non-trivial. This is stuff that I'm working on right now.
Okay, let me say two things. My offer to you when you gave a talk in this series still stands, that I'll come and visit you whenever the pandemic finishes. Unfortunately, I don't see that happening. The other issue, which is more straightforward, is I could, instead of presenting this quantity, I could have just written down for you the integral d phi, phi of x, phi of y, e to the is phi. And just ask, how do I make sense of that object? What this one does, it allows me to make sense of all the Green's functions simultaneously. But as far as a single Green's function is concerned, I just do the path integral over the two phi's with no j in it, and then it's just a plain path integral. It's not a functional. It's not a functional integral.
Okay, Philip, just a very brief remark. The point here is that from a computational point of view, what you do is treat this as a generating function. And what that means is that you expand in powers of j.
Yes.
Okay, and you take derivatives with respect to j and derivatives with respect to j and set j equal to 0.
Yes.
Okay? And that gives you a generating function for the Green's functions. And this is a compact way of defining all the Green's functions.
Yes.
That construction doesn't necessarily work.
Yes,
Okay.
but it's not necessary. It's not needed. I can define the path integral for Green's function by Green's function directly. I don't need to have derived it from a functional integral.
Okay, we have to discuss this because all of this is extremely non-trivial, and the the question of existence is a rather deep question here.
Oh, no dispute. No dispute.
Duncan, Joshua, and Frida are still having questions. Duncan.
Yeah, thank you, Philip, for a nice talk. Can I just, so I have two little questions really, but the first one is underneath your equation 39.
Yes.
You say that S classical phi is classical action as evaluated on each classical path that's integrated over. And maybe we have a different understanding of classical paths, but I would say every path, so that the path integral shouldn't just include classical paths, paths, that trajectories you get from solving the Newton's equations.
Oh, no, they're not stationary. No. Okay, the word classical is often used to mean stationary.
Okay, fine.
I don't mean stationary.
Okay, yes. So that's just the correct. The other point is very nice talk, but there wasn't a picture in it, and so.
Oh, that's a statement about my skills.
but so often we talk about Higgs mechanism and things like that in terms of these Mexican hat potentials, and so I'm wondering,
yes, if
you or someone has nice pictures of what happens to the Mexican hat potential in these three different scenarios you set out. The non-Hermitian generalization of it for someone like me who needs a pictorial.
Okay. The person to ask is Jean, but the Mexican hat doesn't, it'll depend on the parameters, obviously, the shape of the hat. The generic shape of the hat is driven by this term here, the key one, this term here. That's the thing that means that the potential goes to plus infinity at large phi. The hat itself will have different shapes as you change these m1s and m2s and u squared, but it will always be something like a broad rim Mexican hat, but it may have more structure. I've not constructed it.
In all of the scenarios, you still get this sort of zero. You can still go around the brim. You still have
absolutely. That. There's always one long range brim, and the reason there's one long range brim is because the non-trivial minimum is space-time independent. Therefore, it's the same everywhere. Yes, there's always going to be one. There's always going to be one gully. Yeah.
Thank you.
Yes.
Joshua and then Frida.
Hi, everybody. Yeah, let me just open the. Yeah. Hi, Phil. Thank you for your talk. Hello. Yeah, I just wanted to make a quick comment following what Uwe was asking and Carl just before Duncan about path integral. I still don't understand what you path integral 39 computes, what kind of amplitude it computes. And I wanted to point out, in addition, that about a year ago, almost 2 years ago, Fabio and I published computation of path integral quantization of a variant of the Swanson model, where everything was clear. We constructed the path integral using coherent state, or more precisely those I forgot the name, those special coherent states that Fabio likes, and also showed that it produces the same result with ordinary coherent states. And then we also checked the connection between that coherent state path integral to Feynman's path integral, where we showed the necessity of using the correct metric. Everything was clear there. You know from which state you start, you know to which state you propagate. And in the Feynman path integral, lo and behold, you needed complete sets, as Uwe mentioned, complete sets of left and right eigenvalues. And then with such construction, we know that the path integral indeed computes probability amplitude for propagating from A to B. In your equation 39, I don't know what it propagates. It's just mnemonic.
Okay.
Mnemonic
Okay, no. 39 as it stands, before I take derivatives with respect to J, is giving me the energy of the vacuum. Basically, what is happening is...
No. How do you know it gives you the energy of the vacuum? How do you know that?
Because that's what adiabatic switching does. Basically, what happens is you start out with a vacuum without J, you switch it on, you switch it off, you get a phase.
That's all true, but yeah.
I mean, all I've done is I've taken the normal Gell-Mann-Low adiabatic switching procedure and replaced the Green's function by the path integral.
I've done things, I've seen things. Don't Gell-Mann-Low me, please.
You asked me what it is, and that's
you should tell me, how do you know that in your non-Hermitian, Gell-Mann-Low is for Hermitian theories? How do you know?
On the face of it, but there's nothing in it. There's nothing in it that involves hermiticity, except the assumption that the vacuum energy that you get will be real.
No. And Gell-Mann-Low is an ordinary QED, Hermitian theory, where there is
but the switching procedure doesn't involve hermiticity.
Fine, but which space of states are you acting on? That's what Uwe was asking, and what Carl was discussing.
Okay, I will try to
answer either of them, and now you don't answer me.
Okay, well, I did answer you. I told you that all I ever need to do in field theory is calculate the Green's functions.
Okay.
Yeah, but you will have instanton contribution as well.
I know also how to calculate Green's function, and Green's function, it depends on which space of states you are acting on. You have a Dirichlet Green's function, you have a Neumann Green's function, you have all sorts of Green's function.
Okay, I will state the following. I can take two derivatives with respect to J, set J equals 0, and I've got an interval by 5. That's what I'm calling a Green's function. I am not saying that it is vacuum T phi vacuum. I didn't say that. I said it's a Green's function. It obeys a differential equation. Now you then asked me, can I construct that quantity, that path integral generated quantity, by taking some vacuum, some quantum operator, putting in intermediate states and getting the same answer?
But that's exactly what Carl was asking you. Which space?
And I gave you an answer. The answer is, if I construct the propagator and I determine all the poles in the propagator and I determine all the residues, then I know that answer, because those residues are the matrix element of the field between
Matrix
the vacuum
elements in
and the
which
one particle.
states? Matrix elements in which states?
Okay, now
Joshua, can I just let me just try to can I clarify what is being said here? You can write down a functional integral,
Yes.
okay, like the one in 39. And the key question is, what is meant by d phi? Okay.
Exactly.
Okay. Now that functional integral, we can either try to define that functional integral or construct that integral from a set of states using a quantum mechanical framework, or we can simply say, I don't understand quantum mechanics and I don't understand states and operators at all. All I'm going to do is treat this like a classical object. It's just an integral. It's just an integral, okay? But what is missing in the definition of this integral is d phi. And what is being asked here is, for a different d phi, does that give us a different set of Green's functions? Do the Green's functions themselves depend on the definition of d phi or not? And Philip is saying, no, they don't, because we define the Green's function by simply evaluating what you get if you take different functional derivatives with respect to j and evaluate that functional integral. Okay, now that's the question here. Okay, and so if we never ask anything about a vector space or states or completeness or any of those questions, does this functional integral in 39 define, well, are there a well-defined set of Green's functions or not? And that's the question here. What is the minimal amount of information we need to know to uniquely define the Green's functions?
Okay, I'll give you the answer that I always say. If you could have asked an earlier question, which is this: suppose I give you an action, and I ask you, do a variation of the action and get the equations of motion, Euler-Lagrange. Question: over what basis did you do that variation? And the answer is, it's a complete basis of configurations which go from the initial point to the end point. Then the path integral is to integrate back over that self-same set of the same basis that you use for Euler-Lagrange. That's how I define it.
But Philip,
it's not any
even for a quadratic action, this object which you have written down doesn't exist without any I epsilon prescription. This is just meaningless. So you have to say something what you write down. And the general path integral has not only an integration over phi, it has also an integration over the momentum. So the canonical path integral goes even further.
Okay, what is happening is, without it's two questions. One is, if I have here phi, what possible quantum quantity could it be equal to? It can't be equal to the 2-point function, vacuum phi of x, phi of y, because the path integral phi of x and phi of y are classical and can be interchanged. If it were equal to the 2-point function, you would be correct. It would be, you would have shown that that vacuum phi x, phi y vacuum is equal to vacuum phi y, phi x vacuum. It's not equal to the 2-point function. It's equal to the time order product in the quantum language. And that means you need the I epsilon in the classical path integral in order to get it to exist. Without the I epsilon, this is just an oscillating function. It's the I epsilon that in the classical path integral that is needed. First, that's the first thing. You've got to have the I epsilon. And secondly, you've then got to find a basis of d of phi for which it then exists. But without the I epsilon, these are just oscillating functions. So yes.
Maybe I make my question, which I asked.
Yes, I agree. Yes, I agree. I have to use the I epsilon. I always do. Yes.
May I make my point or a question?
Yes, of course.
Or is this this discussion already settled. One thing is a comment. In 2003, I related operators to complex variables. I related operators to holomorphic and anti-holomorphic functions. And so I came to this idea of what you stated about Cauchy relations. Nowadays, I'm now able to construct for non-Hermitian Hamilton operators coherent states which somehow get as an eigenvalue these complex functions, and I can construct path integrals with these non-Hermitian operators. So I think when you come from the operator level, the path integral is very well defined if you are able to construct coherent states. The other direction which Carl asks is I think much more tricky. But my point is now not about this path integral here, but about one of the last sentences you made. You were talking about the zero norm state, which is not observable. There was a long discussion in particle physics about the Z=0 compositeness condition. The question is, are states with zero norm not observable? So when a rho meson decays into two pions, you see maybe the pions as asymptotic states, but in scattering theory, you see the rho meson as an intermediate state which somehow is unstable. So my question is, does this statement, a zero norm state is not observable, still hold in a PT symmetric quantum theory with states which obviously have complex masses? I think this statement is not anymore true.
Okay, well, that's what I claim to have shown. But going back to the Z=0, there you are working in a positive definite Hilbert space, and you're doing radiative corrections and you're calculating wave function renormalization. And you get that Z, because Z goes like 1 over log lambda squared, you get that Z goes to 0. But that's a property of perturbation theory. Now, the question is, and this is the whole thing that led to the Gell-Mann-Low eigenvalue and to the renormalization group, is could the sum of the series give you a finite renormalization constant? Now, I go out on a limb and I say that field theories in which you don't get finite renormalization constants are not relevant to the real world. That's my extreme position, and that's why not only do I work in conformal gravity, which of course is the thing that got me into PT theory, I also am working with in the scale invariant theories where I'm at a fixed point. Conformal invariance actually doesn't really make sense unless you're at a fixed point. But if you're at a fixed point, then you get finite wave function renormalization. But nonetheless, I don't think that's got anything to do with zero norm states, because the zero norm states that I'm referring to are occurring in a non-diagonalizable Hamiltonian in a Hilbert space which does not have a positive norm, whereas the wave function renormalization is occurring in a Hilbert space which does have positive norm. And it's just a statement about the how good radiator, how to what extent can you rely on radiator corrections?
Well, I had a long discussion with somebody about the deuteron as a bound state. Can you observe a deuteron because it never decays? Yeah. What is a composite state? Yeah. From the side of quantum theory, it would have, in a sense, zero norm if you look at it. Yeah.
No. If you just do proton-proton scattering, you produce a deuteron, and a positron, and a neutrino.
But in the moment you couple, something to the deuteron, it's not anymore a bound state.
The deuteron is a bound state in the proton-neutron system. Absolutely, and it's got 2 MeV of binding energy. But if you explore, if you you can photo-disintegrate a deuteron if you come in with more than 2 MeV energy in the photon, and then you break it up into the neutron and proton.
Yes, but here we are with your actions. I mean, you you had these Lagrangians with Goldstone bosons and other states. In the moment you couple your system to something, suddenly such states which you are thinking they are zero norm, maybe they are still observable, even if you have this extreme position, they are not.
Well, as far as I can see, I'm prepared to explore further the issue of the degree to which a zero norm state might be observable. All I've done is I've said that, look, it doesn't carry any probability. It won't show up in a detector. That's as far as I've gone on that subject. I'm amenable to going further. I don't know that the theory, the whole issue of the observability of zero norm states has been explored fully. It looks to me like they won't be. I've also gone out on a limb and said that I think that they're the reason why the wave function collapses is because it emits a lot of zero norm states that we don't see, and therefore we think it's collapsed. So, and the reason I do that is because the graviton in conformal gravity has zero norm. And that's the, I mean, I think that's, there's a lot more in that than I can possibly hope to pull out of. Yes. But what you're really saying is once you get into this issue of non-diagonalizable Hamiltonians, you have to revisit a lot of the notions that we have in quantum field theory. In fact, I'm not sure that there's any that you don't have to revisit. But all I was trying to say today is that it gives you a possible escape to the Englert-Brout-Higgs mechanism. It gives you a possible escape to the Goldstone theorem. And that's the result. That I mean, I wasn't expecting that when I did the calculation. I was quite surprised, and that's why I published it. But it is a very unusual outcome, independent of whether or not that zero norm state turns out to be observable. What would happen in the gauge theory case is you'd see a massless gauge boson with two components and some zero norm Goldstone boson, whatever it is. Even if it is observable, it will not be observed as the third component of the gauge boson. And that's the point I'm trying to make. But yes, there's a lot more to do.
Should we wrap it up here? We have almost covered 2 hours now.
Okay, I'm fine.
Any last comment, last question? If not, then let's thank Philip again. Thank you.
My one apology is okay, thank you. My one apology is I didn't quite catch who was speaking, and I may have got people's names mixed up. So it wasn't, because I couldn't see the gallery at all with the full screen. Yes. Okay.
Okay.
Thank you very much. And also, Philip, if we may ask you the slides, please, it would be nice.
I can send you the slides.